My name is Ian Dennis Miller. I have a PhD in psychology and years of experience working with language models. Along with some friends and colleagues, we've recently launched a new project called Common DevOps. As part of this new work, we're examining the role of language models in software development. And last week, I got into a conversation with Aaron about some of the math and algorithms that make language models go. We recorded this conversation, and in this segment, we discuss the transformer architecture.
So we were just talking a couple minutes ago about influential papers in language models, and I mentioned this one. Attention is all you need. This is kind of the first paper that really presented what we now know as this transformer architecture, the transformer that most of the language models we deal with. This is at the core of it. This Actually, this one you read bottom to top, but this basically describes like exactly what happens to transform the words that you put into the model, at a certain level, to the things that come out. This paper's 2017. All the stuff that happened subsequent to that was like really, really downstream of the transformer. And now, April 2026, a couple years on, we are currently trying to figure out how to use this new model, Gemma 4. This one, Gemma 4 26B. This is a type of model called a mixture of experts model. And actually, this is the same basic diagram that we're just looking at. This pretty much is a transformer here. This right here is a feed-forward neural network. This is called a FFNN. This is a dense neural network. So you might hear people say 31B dense models versus this one, 26B mixture of experts. But anyway, what this is saying here is that there are 30 transformers that are layered basically. And so what I was demonstrating here with the same model, Gemma 4 26B, 26 billion parameters, mixture of experts, I had popped open on Hugging Face kind of the disassembler. This is an inspector for looking at what's inside a model weights file. So we're looking at one format called GGUF that is a kind of a package that keeps everything that you need to run a model all in one file, including things like the chat template and stuff it's required, but it's not strictly the model weights. But down here at the very bottom, uh, this is a description of what is most of the data in the file. When you download one of these files, it's like 17 gigs. This is what most of that 17 gigs is. These are the 30 layers in this picture here, where it says 30x, and that's what these are. These are the 30 things being repeated, and you can inspect all of them, and actually then you can even see the size, how much space essentially is taken up by the weights that define one of the networks. And so I said this is a mixture of experts type model. So this is a matrix here. It is a feed forward network. These are experts. I won't necessarily get into that, but it's another neural network, and it's pretty big in this case. It's actually a three-dimensional matrix, 704 by 2,816, and so on. And part of one of the tricks of actually getting these models to run at home on sort of consumer hardware is to be clever with the bit precision, the number precision for how you've actually written these numbers to the file. F32 is actually it's hovering here, 32-bit standard IEEE floating point number. But this, by contrast, is a very, very quantized approximation of a 32-bit floating point number, but it only takes 4 bits of space. So this could only be a gross approximation. 4 bits is like 16 different values, whereas 32 bits is, there's a ton of precision in 32 bits compared to 4. But nevertheless, it works actually. And the more compressed the model is, typically the more of this matrix will be, or the more of all of these matrices in the network are going to be quantized more intensely than others. So what we're looking at here then is, here's these expert layers. Well, I mean, the whole layer has some experts in it. And if you want to think about how a neural net, how a language model is like literally doing the math to take whatever whatever the input is, and to actually like do math to turn it into some kind of output, that the math is this, and then you take this math and you apply it to these values, these weights. These weights contain the strength of the connection essentially between neurons in the neural nets. If you just think about all that at the same time, that's how the GPU behind me like actually does the math. It's these computations combined with the model weights that, in this case, I'm downloading them from Hugging Face, and there you have it.
So, if you enjoyed that, then stay tuned for more uploads coming from this common DevOps conversation. Thank you very much. See you next time.